Hello students, hello viewers, thanks for watching. So we are going to continue with the study, but before then let's quickly remind ourselves of what is called a definite integral. As you can see on the screen, we have definite integral of x over the interval of 1 to 3. So how do we handle this? As you can see it here, so if we integrate x will give us, if we integrate x, it will give us x squared over 2. Then you can see the interval here, 3 to 1. Okay, so the next thing is that we can bring out 1 over 2. Then it will remain x squared over the interval of 3 to 1. That's what we can see here. So what is the next thing? The next thing now is for us to evaluate the integral. Then we can, the first thing is we first of all substitute the upper interval, which is 3. Then we now say minus the lower interval, which will give us 3 squared minus 1 squared. That is how to handle definite integral. So let's continue with the Fourier coefficient an. On the screen here, we have our 6.1, which you are very familiar with, and we have explained the reason why we don't have b naught here. So let's imagine that, let's try to multiply both sides by cos nx. That is the first thing. We first of all multiply 6.1 by cos nx, and we integrate between minus pi to pi. So that is how we obtain this expression on the screen. You can see the expression now. There's no big deal there. Just multiply both sides of 6.1 by cos nx, then you integrate from minus pi to pi. Now, one thing we should notice here is that whatever that's going to happen to a1 cos nx, the same thing that will happen to a2 cos nx, is the same thing that will happen to this expression. So instead of us speaking it one after the other, we may try to generalize it by considering only the following term that will highlight here: this term, and at the same time this term. So we only need to integrate the 3, then we substitute them back into this expression. Let's start from the first one, which is our 8.1 now. Here we want to integrate fx cos nx over the interval of minus pi to pi. So which is our 8.1. So then we can see now that this one is equals to this. Those are the ones that I've highlighted yellow. So let's start with the first one, which is this term. Let's start with this term. Okay, here if we integrate cos nx, what we get is sin nx over n. Okay, then you evaluate it over the interval of minus pi to pi. So that will give us a naught over n. Then we have sin n pi. We are trying to evaluate the upper interval, then minus pi. This minus pi here is minus n times minus pi. So we have it there, and that's what. So the next thing is for us to remember that we need to handle this expression, which is a sine minus n pi. And because we know that sine is an odd function, what we are going to get here is that sine minus n pi is equals to minus sine n pi. Why? Because sine is an odd function. That is how we obtain this expression here. So if we substitute this one back to this expression, we now see now that this one here will give us a naught over n, then sine n pi, then minus this minus that is outside before is still here. Then this one is because sine minus n pi is equals to minus sine n pi. So we have this expression. Now we can proceed, and this time this minus times minus will give us plus. We give us minus times minus will give us plus. That's how we obtain this plus here. So we have sine n pi, and don't forget we have this. So if you add this together, it will give us 2 sine n pi. That is how we obtain this expression. So we can now see now that these 2 will come outside. Then we have a naught over n. But don't forget the periodicity property of sine n pi, which means that at any integer n, sine n pi will always be 0. So which means that if that is the case, then definitely everything here will give us 0. Then we can say that integral minus pi to pi a naught cos nx dx is 0. That is how we obtain 8.2. 8.2 here is actually the first term here. So we need to proceed to the second term of right hand side of equation 8.1. So let's proceed. Next term is this. So we want to evaluate definite integral an cos nx dx. So there's a problem here, and it's not really a problem, it's just a simple arithmetic trigonometry property that we are familiar with. The reason is because this integral here, it has to do with n here and this n here. In fact, we are going to consider two different cases, but before we proceed, let's consider this. Cos a plus b, which is what we can see on the board. You know, we are familiar with this before in MTS 101. So what about a minus b? A minus b will give us this expression. So what is the next thing now is that, you know, we're actually looking for cos nx. So for us to get this, we can actually add the two together. So if you add the two together, we're going to obtain this expression, because by the time you add it together, this term here, we cancel this term. Okay, it will cancel. So by the time this and this cancelled, what we have now will now be 2 cos a cos b. Then we add this together. That will give us this expression. So we are now very good to go now. Let's try to now make this one to give us cos ms cos nx. Why am I using m? The reason is because the integral 8.3 here, it has to do with the value of the integer n here. Let me try to highlight it in red color. Okay. So this integer here, it will determine the outcome of this definite integral. So that is the reason why we want to consider multiple cases. If whatever that may happen to n and n here, because they are integers and they will determine the outcome of the definite integral. So let's change one of them to m. So we now have cos mx cos nx. So back to expression here, you know, here you can divide this one by 2. Then we have this expression here. So let's consider the first case. The first case now is when integer m is not equal to integer n. Let's consider that. So we now have minus pi to pi an cos mx cos nx. Then that will give us an over 2. We are now using this expression now. An over 2 integral minus pi to pi cos mx plus nx. Then we have this expression. So what's the next thing? We integrate. Don't forget, by the time you integrate cos mx plus nx, what you have is sine m plus n into bracket x, then divided by what? M plus x. Because you need to differentiate this. Remember, okay? If you differentiate mx plus nx, what you have is m plus n. So we do for the other one too. Then we evaluate the integral. So when we evaluate the integral, we need to use the upper bound first. So look at the first upper bound now. This is for the upper bound. We have for the upper bound, which is pi. Then we have for the lower bound, which is minus pi. You can see now that after the integration, wherever you see x, you put the upper bound there, then minus. I think I've explained this one at the beginning of this video where I was talking about the definite integral. So we have minus pi for the lower bound of the interval. So remember, sine n pi, which is an odd function, it will give us minus sine n pi. So what we're going to do is that we come to this expression, and then this expression. You can now see now that instead of having minus pi, we are now having ordinary pi, but there is minus outside because we've used the concept of the fact that sine n pi is an odd function. So that is why you can see now that we now have minus. So we have this. What's the next step? We multiply minus times minus will give us plus. We multiply this one again, minus times minus will give us plus. So that is that. So the next thing now is that we now note that we can add them together. So if we add this, let me change it to color. If we add this and you add it to this, what we have is 2m plus n divided by m plus n pi. That is for the first one. Then the second one is that if you add this, let me highlight it in green. If you add this to this, what you will get is this expression. You get it? So we are good to go. Then the next thing is this. We still need to go back again to the fact that sine m plus n pi is still an odd function. Even the same thing applicable to sine m plus n pi, which is also an odd function, because m plus n here is an integer. If you add integers together, what you get is an integer. If you subtract integer from one another, you get integer. So, and at any value of this integer, this expression here will give us 0. So by the time you substitute 0 there, you can now see now that we obtain 8.3, because this is 0. This is also what? 0. Then we have this expression. This one is for the case when m is not equals to n. I think you remember this. That's the first case. Now let's go to the second case again. The second case now is when m is equals to n. So how do we go about it? We go back to the expression before, which is this that we're familiar with. That is when we added these two expressions together. Okay, so let's proceed. But this time around, m is equals to n. And if m is equals to n, which means that this expression here, they are the same thing. This expression here, they are the same thing. So if you add the same thing together, you will have mx plus nx. Let me highlight it in yellow. And by the time you subtract the same thing, what you get is what? You get 0. That's why we obtain cos 0 here. So don't forget, cos 0 is what? Is 1. So mx plus mx will give us 2mx. Then if you multiply this one, it will give us 2 cos square mx. Please pardon me, I'm supposed to put a bracket here, but I believe you understand what I'm doing here. So back to this expression. But remember that there is other way that we can use to obtain this expression. Let me highlight it. There's another way again that we can use to obtain this same expression. What is that way? We go back to the addition of cos a plus b. You have this. Then you now say let your a and b to be the same thing. And when they are the same thing, you have this expression. Don't forget that cos square nx plus sine square nx is equals to 1. And from there, we can actually make sine square nx to be the subject of formula to give us 1 minus cos square nx. Okay, so if you return this one back to this expression, you have this. Then you can now see now that we can still obtain this same expression with this. So what are we now trying to do now is that if we are evaluating the same integral, which is this integral, and we are considering the fact that the two integers, they are the same, so we are going to obtain this expression, which means that they are the same thing. Look at it now. Look at it. So, but remember that cos 2nx plus 1 is equals to this. Because look at it. What I'm trying to say here is that cos nx multiply cos nx multiplied by cos nx. Cos nx multiplied by cos nx will give us was cos square nx. And if you have cos square nx, is the same thing as this expression. So we can now integrate this, which we are familiar with. So by the time you integrate cos 2nx, what you have is sin 2nx over 2n. Then by the time you integrate 1, you have x. Then you evaluate over the integer over the interval of minus pi to pi. So you now have an will come outside. Then this one, you first of all substitute the upper bound of the interval. So upper bound of the interval. Then this is for the upper bound of the interval. Then the second one again, we use the lower bound of the interval. We use the lower bound of the interval, and this is the other one for the lower part of the interval. So we have this expression. Then remember the property that sine minus 2n pi is equals to minus sine 2n pi, because sine is an odd function. So we substitute it back to the expression. Then we add it together. Then we have this expression. What am I trying to do here is this. If you add this to this expression, what we get is 2 sine 2n pi over 2n. Then by the time you add pi to pi, you have 2 pi. So remember again, sine 2n pi is also 0 for all the values of integers for 2n. So you substitute it back to this expression. So we have this equation 8.3b. So what have we done so far so good is that for this expression, we've been trying to use the fact that there are two cases for this particular definite integral. Let me highlight it in green color. Oh, no, not everything. This expression, that there are two cases. We've considered the first case when m is equals to n. which is this expression, and we also consider when m is not equals to n. When m is not equals to n, what we obtain as 8.3a is 0. And when we consider the case when n and m, they are the same thing, we have an pi. We have an pi. So let's proceed to the last term of equation 8.1. Here we want to evaluate minus pi to pi bn cos nx cos sin nx then cos nx ds. But see, it's very simple. Let's just go back to what we are familiar with before. Addition of sine and cos and sine. So we have sine n plus m, sine n minus m. So we have this expression here. Then we consider the fact that we can add them together. So by the time you add them together, this expression here, we take care of this expression here, the one I highlighted in green color, they will cancel. So by the time they cancel, then you can now have sine nx cos mx to give us this. So let's consider the first case as well. That is when m is not equals to n. So when m is not equals to n, we have this expression, just like I've explained before. You just integrate, then you evaluate the interval. So, but here, we are going to consider the fact that cos is an even function. So why? Since it's an even function, we see that cos n plus m minus pi will give us positive, because there's plus here that we don't write. Cos n plus m then pi. So you substitute. By the time you substitute, you add them together, you will just discover that this one we cancel this one we cancel this. Then you have it to be 0. That is when m is not equals to n. Let's consider the case of when m is equals to n. You follow the same procedure again, then you have this expression, but you consider the fact that sine 0 is what? Is 0. So if we do that, then you can see that we are going to obtain this expression, then we have this, then we can now see clearly that an is indeed equals to 1 over pi minus pi to pi f of x cos nx dx, because from this expression here you can make an the subject of formula. So by the time you do that, you have your equation 8.7. So we can now proceed to tutorial question 8.1, where we're going to consider the fact that if fs is cos 10x, then we should find our an. So that is how to obtain the Fourier coefficient an. Thank you very much for watching. Thank you. Bye.